Today, we are going to learn about phase transitions. This is going to be our fourth lesson in States of Matter unit. So our learning targets, by the end of this lesson, you should be able to define what phase transitions are and some of the temperatures at which phase transitions occur. You also should be able to explain the relationship between phase transition temperatures and intermolecular attractive forces. So first, we're going to talk about vaporization and condensation. These are some words that you probably have heard of before. Condensation is what we call a change from the gas phase to the liquid phase. So we go from gas to liquid. We call that condensation. So when anything goes from gas to liquid, that's called condensing or condensation. Vaporization is the change from the liquid to the gas phase. So it's going to be anything that goes from its liquid phase into its gas phase. For example, like water boiling is going to be an example of vaporization because the liquid particles of water are becoming gas particles. Dynamic equilibrium is when the rate of condensation is equal to the rate of vaporization. So this is going to be when the same number of particles are becoming a liquid as the same number of particles that are becoming a gas. So if you kind of were to look at like a closed water bottle, that would be an example of something in dynamic equilibrium because it would have some evidence of condensation on the sides of the water bottle up near the top, where you'd see kind of like some collection of water droplets. That's going to be your condensation occurring as a result from vaporization as well. And then we also have something called vapor pressure. Vapor pressure is pressure exerted by the vapor. So like gas vapor is going to be a gas. So pressure exerted by gas that is in equilibrium with a liquid in a closed container at a given temperature. So vapor pressure, for example, would be the pressure of water vapor inside of a closed water bottle. So there is a slight pressure from the water that has become water vapor, and it's putting a pressure on the surface of the liquid in the water bottle. So just some images to kind of understand vaporization and condensation a little bit more. In A, we see we've got liquid and we have the particles starting to they're just starting to come up or escape the surface to form vapor. So right here, we're going to see vaporization occurring. The particles are starting to escape the surface of the liquid and become particles as vapor in the liquid. So in a closed container, dynamic equilibrium is reached when the rate of molecules escaping from the liquid to become gas. Eventually, we're going to start to see more molecules begin to escape the liquid and become even more vapor molecules. So that's what we're seeing here in letter B. So letter B is increasing amounts of vaporization. And then letter C is when equilibrium is reached. Vapor pressure can be determined at this point, and this is another manometer, but this one, instead of it being just a gas, it's a liquid that allows vaporization to occur. So here we've got even more particles of vapor that you can see, and that's actually they've equaled in equilibrium. So the vapor pressure of the gas is constant, and the vaporization and condensation continue. So you'll see particles are going to vaporize, and then also some of these vapor particles are going to condense and go back to the liquid. So you'll see some droplets collecting on the sides of this container, and those droplets will move down back into the liquid. So you're going to see an equal amount of particles becoming vapor and also an equal amount of particles becoming liquid at that stage in equilibrium. So molecules with high intermolecular forces, so things like a lot of dipole-dipole interactions or hydrogen bonds, things like that. These molecules that have a high number of intermolecular forces are better at recapturing the gas phase molecules when those molecules collide with the liquid surface. And so molecules with a high intermolecular forces are going to have low vapor pressure because their higher intermolecular forces are going to recapture those gas molecules and pull them back into the liquid. Molecules that have low intermolecular forces are going to have less of a barrier to vaporization because there's not going to be as much surface tension, as much adhesion and cohesion. So they're going to have less likelihood of recapture. And so you're going to see a higher vapor pressure because you're going to see more particles escaping the surface of the liquid and becoming vapor, and less particles going back into the liquid phase. A higher temp usually equals higher vapor pressure because you have increased kinetic energy. As you add energy to molecules, they begin to move faster, they collide more often, and that's going to lead to an increase in pressure, which is where we get our higher vapor pressure with a higher temperature. Lastly, another word that you probably have seen before, but we haven't talked about, is evaporation. So evaporation is vaporization, so going from liquid to gas, but this occurs when the surface of the liquid is not boiling. So evaporation would be something that occurs like in the outside natural world. Like for example, if we have a puddle of water, that puddle of water is not going to boil, but it's still going to dry up, and you're still going to see that the water is going to become gas particles, and it's going to release to the atmosphere. Evaporation also occurs in our perspiration when we sweat. It's actually a cooling process. So it occurs as the liquid's temperature decreases. So that's what we see with evaporation. It is a cooling process. So as particles are escaping, they're bringing their high energy with them, and as they bring the high energy with them, they're actually lowering the temperature of the liquid or lowering the temperature of the substance. So, for example, when we sweat, sweat is going to be liquid, and sweat's job is to actually pull heat out of our body. So as we sweat, what's going to end up happening is that sweat is going to start to evaporate off of our skin. And as it evaporates off of our skin, the hotter particles, or the particles that have more energy, are going to be hotter, and those are going to become vapor quicker, and they're going to leave off of your skin. And as they leave off of your skin, they're taking that energy with them, which coincides to actually cooling you off and cooling off the liquid sweat that's still left remaining on your skin. So that's an example of how evaporation is actually a cooling process for the liquid, because it removes heat and removes energy from the liquid by taking the higher energy molecules out. So this is a diagram that kind of shows vaporization and condensation, and temperature, low temperature versus high temperature. We've got number of molecules on our y-axis and kinetic energy on our x-axis. So as you can see here, temperature does affect the distribution of kinetic energy of molecules in a liquid. So when there's a higher temperature, we're going to have more molecules that get the energy that they need to escape from the liquid phase of the gas into the gas stage. And when we have a lower temperature, we've got less kinetic energy, as you can see. So it's going to take more of an increase in temperature, or more molecules, to be able to get into that gas phase. So that's all that this diagram is showing you. So now you've got a question to answer on this Edpuzzle. Do you think it's true or false? When adding heat to something that is evaporating, the temperature will increase. So this is actually false. When adding heat to a substance that is evaporating, it will not increase the temperature. Instead, all it does is increase the kinetic energy of the molecules. Once all of the molecules have enough kinetic energy to break their intermolecular force bonds that are holding them in the liquid state. So for example, break the bonds that are causing cohesion and adhesion that are keeping them in the liquid state, they will then enter the gaseous state and increase in temperature afterwards. So evaporation does not it's not caused from an increase in temperature. Instead, it's an increase in kinetic energy. So common misconception is that things increase in temperature as they're evaporating. But like I said earlier, evaporation is actually a cooling process. As things evaporate, you actually are going to see a drop in the overall temperature.
Are we working on?
Our next set of definitions is going to be about boiling point. So boiling point is when vapor pressure increases enough to equal your external atmospheric pressure. So remember, vapor pressure is going to be the pressure of like vapor particles above a liquid. So for example, if we had a jug of water, it'd be the pressure of the water vapor particles above the jug of water, the liquid water. So boiling point happens when vapor pressure is equal to external atmospheric pressure. So when those become equal, something will actually boil. So we have something that's called normal boiling point. And this is a boiling point when the atmospheric pressure is 1 atm, otherwise known as 101.3 kPa, which is one of our STP units. At lower atmospheres, the boiling point decreases because there's less external pressure. And at higher atmospheres, the boiling point increases because you're going to need to have more energy to overcome the surface pressure in order for those molecules to be able to overcome the surface of the liquid. As a reminder, when something is boiling, the temperature does not change if heat is added. Instead of the temperature changing, the kinetic energy is increased and the vapor pressure is increased. So just another point to remember here. And then obviously the at lower ATM and at higher ATM, these are going to be very important points as well. So just looking at some common liquids and their boiling points, we've got ethyl ether. Ethyl ether has at a pressure of our standard pressure, which is 101.3 kPa, has a boiling point of below 40 degrees Celsius. Humans actually run at roughly 32 degrees Celsius. So ethyl ether almost boils at the temperature that humans are at. So it's a very, very low boiling point. The next one we have is ethyl alcohol. So this is going to be something like rubbing alcohol or something similar to that. At your standard sea level pressure, it's going to have a boiling point of 80 degrees, so less than water. And then if you look at water, obviously at 1 atmosphere of pressure or at sea level, we know water is going to boil at 100 degrees Celsius. And then our bottom one, this one down here, ethylene glycol. This is actually a substance that's commonly found in like vape juice and vape products. And it's one of the reasons that people are so afraid of it is because it has a very high boiling point, which means it's very likely to remain as a liquid in your lungs because our lungs are not at any of these temperatures. So it's actually not going to be existing as a gas substance inside of your body. It's going to cool and condense back down to a liquid substance, which is why vape juices and things like that are so hazardous to our lungs, because you get sticky substances like ethylene glycol that stick inside of your lungs. So as you can see here, ethylene glycol has an extremely high boiling point. So question for you, what has the highest boiling point at 1 atmosphere of pressure? All right, next we've got melting and freezing. So melting is obviously going to be transitioning from solid to liquid state. And energy is going to need to overcome the forces that hold the solid together. So we've got forces, intermolecular forces, that are holding the solid particles together. And in order to get to the liquid state where those particles are able to free and they're able to move in a more flowing manner, they're not in a rigid shape, we need to break those intermolecular force bonds. So we're going to need energy in order to melt something. The temperature of a solid stops raising or rising and remains constant until all of the solid is melted. So for example, like if you're melting ice, if you heat up ice, the temperature of the ice water as you're heating up ice should remain constant even if you're adding heat to it. Instead of the energy going into raising the temperature of that liquid with ice in it, instead that energy is going to be used in the ice particles, and it's going to be used to break those intermolecular force bonds to allow those particles to move more freely and become in the liquid state. So adding heat actually just increases the amount of energy, and it breaks the intermolecular force bonds that hold the solid together. Once all of the solid is melted and all those intermolecular forces that were holding something in a solid state are broken, the temperature of the liquid will then increase once everything has gone from the solid state to the liquid state. So this is just kind of an example of this. Here we've got a beaker of ice, and the beaker is getting heated over time. As you can see, the measurement on the ice in the beginning is negative 12 degrees Celsius, and it's staying in ice form. On picture B here, we've got a little bit of ice and some already melted water down at the bottom, and you can see it reads 0 degrees Celsius. As you move along, more liquid, but still some chunks of ice, it's still at 0 degrees Celsius. So as you can see from these measurements, until all of the liquid has finally, or all of the solid is finally melted, we're not going to see an increase in temperature. So we finally see the increase in temperature here in picture D, where there's no ice remaining, it's only liquid. And now we're going to start seeing a climb in temperature as we add heat to this liquid. Freezing. Freezing is obviously going to be a transition from liquid to solid state. So we're going to go from liquid, a more free state, to a more rigid solid state. Temperature of a liquid is going to stop falling, and it's going to remain at a constant threshold until all of a liquid is frozen. So it's opposite of melting. The temperature is not going to change once things start to freeze. Instead, the temperature is going to remain constant of that substance until everything has finished freezing. So the temperature is not going to change once freezing point is reached. Instead, more intermolecular forces are going to be forming that are going to bring the liquid into the solid state by putting it into more of a rigid type of shape. Once all of the liquid is frozen, the temperature of that substance will then start to drop if heat is removed from this scenario or the substance. So melting and freezing point. Melting point is going to be used when we talk about solids. So it's going to be the temperature at which a solid and liquid phase of a given substance are at equilibrium. So if we're talking about melting point, that would be like if we got a glass of ice cubes and we set it out. Once the ice starts to melt, the temperature of that ice and liquid water substance is going to be the melting point, and it's going to be in equilibrium until, like I stated earlier, all of the ice cubes have melted. Then you'll start to see the temperature of that system increase. Freezing point we use when we're talking about liquids, and this is the temperature when a solid and liquid phase are at equilibrium. So if I took a glass of water and I put it in the freezer, once that water starts to freeze and become solid, you're going to notice that the temperature is not going to change, even though we have liquid and solid in there. The temperature will not change until all of the liquid has entered the solid phase, and then you will see the temperature continue to drop in that system. So another true and false question for you. Adding heat to something that is melting is going to increase the temperature. So do you think that's true or false? So that is actually a false statement. Adding heat just increases kinetic energy of the molecules. And remember, kinetic energy is going to be energy of movement. So adding kinetic energy is going to allow these molecules to break the IMF bonds that are holding them in the solid state. Once all of those intermolecular forces that keep the molecules in the solid state are broken, the substance will then be in the liquid state, and then you'll see more flowing of the molecules and the atoms moving in that substance, and you will then see a temperature increase in that system. All right, our last topic is sublimation and deposition. These are words you probably have never seen before, so some newer words for you. Sublimation is a solid that transitions directly into a gas. It skips the liquid state altogether. So a good example of something that goes through sublimation would be like dry ice. Dry ice is actually solid carbon dioxide, and dry ice goes from solid, that dry ice, that very, very cold block of carbon dioxide, straight into carbon dioxide vapor at room temperature. And I've got a picture of it down here. If you've never worked with dry ice before, think back to like when you were in elementary school, the fog that came out of the punch bowl that parents made, that was from dry ice. So that was actually an example of sublimation occurring. And then lastly, we have deposition. Deposition is opposite of sublimation. It's when a gas goes straight into the solid state and skips the liquid state. So an example of this is actually the formation of frost. So frost actually occurs because of water vapor that sinks low at night during nighttime. So it sinks low, and as temperatures decrease during the night, the water vapor is flash frozen, and then frost is actually what we have as a byproduct of that. So frost is an example of water vapor that gets frozen directly into ice. Two things that you're going to answer. How do you connect this into our own life? How could you connect any of these things that we learned today into your everyday life? And what is something that you found interesting from today's lesson? And the last question I have for you is, what is the most important thing that you thought that you could have learned from today's lesson?